There are moments in astronomy when routine becomes revelation. When a telescope designed to catalogue ordinary objects catches something that should not exist. On July 1st, 2025, that moment arrived. An observatory in Chile was scanning the night sky as it does every clear evening. Its cameras sweep across thousands of stars each hour, searching for movement. Asteroids leave faint trails as they orbit our sun. Comets appear as fuzzy dots, drifting slowly against the background of space. Most nights, the software flags dozens of these objects. Most are familiar, predictable, already catalogued. But one reading on that July night was different. The object moved across the detector with unusual speed. Its path suggested something the algorithms were not programmed to expect. As astronomers reviewed the data, they noticed numbers that did not fit standard models. The trajectory was wrong. Not slightly off, but fundamentally different from anything bound to our solar system. Over the next 48 hours, telescopes around the world confirmed what seemed impossible. This object was not circling our sun. It was passing through. A visitor from interstellar space. The third such object ever confirmed by human observation. They named it 3I Atlas. 3I for Third Interstellar. Atlas after the telescope that found it first. Within days, the scientific community began noticing details that separated this visitor from its predecessors. It traveled faster than any interstellar object previously recorded. More than 60 kilometers per second. Roughly twice the speed of the first interstellar visitor discovered in 2017. Early observations revealed a coma, the glowing cloud of gas that surrounds active comets. But the chemistry was unusual. Spectroscopic analysis showed concentrations of carbon dioxide far higher than water vapor. A ratio never seen in any comet originating from our solar system. The strangeness did not stop there. Most comets remain dormant until they approach the sun closely. Heat from sunlight causes their ices to sublimate, creating the familiar glowing tail. Atlas was already active at distances where most comets stay frozen and quiet. Something about this object was responding to conditions differently than expected. Scientists calculated its origin based on trajectory and velocity. The path suggested it came from regions of our galaxy populated by ancient stars. Stars formed billions of years before our sun existed. If the calculations were correct, this object had been traveling through space longer than Earth has existed. It carried within its frozen nucleus a record of conditions from an era we can barely imagine. News of the discovery spread quickly, but the tone of the coverage was cautious, almost careful. Space agencies emphasized safety. The object would pass at a comfortable distance, more than 270 million kilometers from Earth. There was no danger of collision, no risk to our planet. Yet beneath the reassurances, questions began to accumulate. Why was it moving so fast? Why was its chemistry so different? Why did its trajectory suggest such an ancient origin? And perhaps most unsettling, why did it seem to be active so early? These questions did not point toward immediate answers. They pointed toward possibilities. Some natural, expected, and explainable within current scientific understanding. Others less comfortable. The kind that force us to consider whether what we are observing is entirely natural, or whether something else might explain the patterns we are seeing. Interstellar objects are rare, Until 2017, we had never confirmed one. Now, within less than a decade, 3 have appeared. Each one stranger than the last. The first, Oumuamua, sparked debates that continue today. Its shape, its acceleration, its silence all created room for speculation. The second, Borisov, behaved more predictably. It looked and acted like a comet should, offering reassurance that interstellar visitors could be ordinary. But Atlas has reopened the questions, not through dramatic anomalies, but through subtle accumulations of strangeness. Details that individually seem explainable, but together create a pattern that resists easy interpretation. Tonight, we will explore what makes this object different. We will examine the data that scientists are studying. We will consider the natural explanations that account for most of what we observe. And we will carefully, thoughtfully, explore the possibilities that remain. The ones that ask whether we might be witnessing something beyond the random debris of planetary formation. This is not a story about certainty. It is a story about observation, interpretation, and the questions that emerge when the universe delivers something unexpected. Atlas is still visible in telescopes as it moves toward its closest approach to the Sun. That moment will arrive on October 29th, 2025. What happens then may answer some questions, or it may deepen them. For now, we watch, we measure, and we wonder. Because sometimes the most important discoveries are not the ones that provide answers. They are the ones that teach us which questions to ask. Welcome to Info Jungle. If you enjoy calm, thoughtful explorations of science and space, consider subscribing. We create these documentaries to help you relax while learning about the mysteries our universe presents. Let the information unfold naturally as we journey together through this story. Telescopes scan the sky every night. Most of what they find is expected. But every few years, one observation breaks the pattern. July 1st, 2025 was one of those nights. The Atlas telescope system was built for a specific purpose: to detect objects that might pose a threat to Earth. Asteroids and comets that could one day cross our planet's path. The system operates automatically, photographing large sections of sky each clear night. Software compares new images to older ones, looking for objects that have moved. Most nights, the system finds dozens of these moving points of light. Nearly all of them are asteroids already catalogued. Their orbits are known, their paths predictable. Occasionally, a new object appears. Something not yet recorded in the databases. When that happens, the system flags it for human review. Astronomers check the data, calculate a preliminary orbit, and determine whether follow-up observations are needed. On the night of July 1st, the Atlas telescope in Chile captured an image containing a faint object. Magnitude 14, barely visible even through the telescope. The automated system noticed it had moved between exposures. The initial classification was unremarkable. Possible comet or asteroid requires confirmation. But when astronomers began calculating its orbit, something unusual emerged. The object's velocity was higher than expected. Much higher. Most objects in our solar system move at speeds determined by their distance from the Sun. Closer objects orbit faster, distant objects move more slowly. This relationship is predictable, governed by gravity and orbital mechanics. But the new object was moving faster than its distance from the Sun would suggest. At first, the astronomers thought there might be an error in the measurements. Perhaps the time stamps were wrong, or the object's position had been misidentified. They requested additional observations from other telescopes. Over the next 2 nights, observatories in Hawaii, Spain, and Australia all pointed instruments toward the coordinates. Each new measurement confirmed what the first had suggested. The object was moving at approximately 61 kilometers per second. That speed placed it well above the escape velocity of the solar system. It was not bound to our sun. Its trajectory was hyperbolic, the mathematical signature of something passing through rather than orbiting. By July 3rd, the conclusion was certain. This was an interstellar object, something that had originated outside our solar system and was now crossing through it. The discovery triggered protocols established after the first interstellar visitor was confirmed in 2017. Observatories around the world added the object to their observation schedules. Space agencies prepared press releases, and the scientific community began asking the immediate questions. Where did it come from? How long had it been traveling? And most importantly, what could it tell us about the galaxy beyond our solar neighborhood? The object received its formal designation quickly. C 2025 N1, indicating a comet discovered in the first half of July 2025. But once its interstellar nature was confirmed, it received a more distinctive label, 3I, marking it as the third interstellar object ever confirmed. The full name became 3I Atlas, honoring the telescope that made the discovery. News spread through the astronomical community within hours. Emails circulated, phone calls were made, and social media filled with speculation. For most people, the discovery was exciting but not alarming. Another interstellar visitor, similar to the ones detected in 2017 and 2019. A rare event, certainly, but one that fit within the expected possibilities. Space agencies emphasized this normalcy in their early statements. The object posed no threat to Earth. Its closest approach would place it more than 270 million kilometers away, roughly twice the distance between Earth and the Sun. There was no danger of collision, no reason for public concern. But for those who study these objects closely, the initial data contained hints of something unusual. The extreme velocity was the first clue. At 61 kilometers per second, Atlas was moving significantly faster than either of its predecessors. Oumuamua, the first interstellar object, had traveled at roughly 35 kilometers per second. Borisov, the second, moved at slightly less than 33 kilometers per second. Atlas was nearly doubling those speeds. That difference might seem minor, but in orbital mechanics, velocity tells a story. It reveals the forces that shaped an object's journey. Higher speeds suggest more violent ejections from their home systems, or longer journeys through regions where gravitational interactions could accelerate them. Either way, the velocity hinted at a history different from the relatively calm scenarios imagined for previous visitors. The second unusual detail came from early spectroscopic observations. When telescopes split the light from Atlas into its component wavelengths, they saw evidence of a coma. The fuzzy cloud of gas and dust that forms when a comet's ices begin to sublimate. This confirmed that Atlas was a comet rather than a bare rocky asteroid. But the composition of that coma was unexpected. Most comets show strong water vapor signatures. Water ice is abundant in the outer regions of planetary systems, and it sublimates readily when heated by sunlight. Atlas showed very little water. Instead, the dominant molecule in its coma was carbon dioxide. The ratio was extreme, roughly 8 parts carbon dioxide to 1 part water. No comet from our solar system had ever displayed such a composition. Scientists immediately began proposing explanations. Perhaps Atlas formed in a colder region of its home system, where carbon dioxide ice was more stable than water ice. Or perhaps cosmic radiation had processed its surface over billions of years, sealing water beneath a carbon dioxide-rich crust. These explanations were plausible, even likely. But they still marked Atlas as different, as something that would require careful study to fully understand. The third detail emerged from trajectory analysis. By tracking how Atlas moved across the sky, astronomers could calculate where it had come from. Not the specific star system, that remains unknown, but the general direction and the region of the galaxy it had passed through. The calculations suggested an origin in the thick disk of the Milky Way, a population of old stars with eccentric, tilted orbits. Stars formed billions of years ago when the galaxy was younger and more chaotic. If Atlas truly came from that region, it meant the object was ancient, potentially older than our solar system itself. These three details, velocity, chemistry, and origin, painted a picture of an object unlike any comet we had studied before. Not dramatically different, but different enough to raise questions. And questions, in science, are the beginning of discovery. The discovery of Atlas marked the start of intense observation. Telescopes around the world began tracking its path, measuring its light, and analyzing its composition. But as data accumulated, the strangeness of this visitor became more apparent. Details that at first seemed like minor curiosities began forming a pattern that would challenge our understanding of what interstellar objects should look like. When something arrives from beyond our solar system, scientists face a challenge. They must determine what it is based on limited observations. A few weeks or months of data before the object moves too far away to study. With Oumuamua, the first interstellar visitor, that window closed before many questions could be answered. The object moved quickly, and by the time astronomers realized how unusual it was, it had already passed. Debates about its nature continue today, unresolved. With Borisov, the second visitor, the window was longer. Astronomers had months to study it, and what they found was reassuring. Borisov behaved like a normal comet in almost every way. Its chemistry matched what models predicted for comets formed around other stars. Its activity increased as it approached the sun, then decreased as it moved away. It fragmented slightly under solar heating, just as many local comets do. Borisov suggested that interstellar space is filled with objects similar to those in our own system. That planetary formation follows similar patterns everywhere. That the universe, while vast, operates by consistent rules. But Atlas is different. Not in obvious, dramatic ways, but in subtle accumulations of details that refuse to fit the comfortable patterns Borisov established. As scientists study this third visitor, they are finding that each new measurement adds to a growing list of peculiarities. Some explainable, some less so. All of them raising questions about what we are really observing. Let us look at what makes Atlas stand apart from everything that came before it. In space, velocity is history. How fast something moves tells you where it has been and what forces shaped its journey. Atlas moves faster than anything we have seen from interstellar space. And that speed raises questions about its past. When astronomers measure the velocity of an interstellar object, They are looking at two components. First, the orbital velocity within our solar system. This changes as the object approaches and recedes from the Sun. Gravity accelerates objects as they fall inward, then slows them as they climb back out. Second, and more importantly, the excess velocity. The speed the object carries beyond what our Sun's gravity accounts for. This excess velocity reveals how fast the object was moving through interstellar space before it encountered our system. For Oumuamua, that excess velocity was approximately 26 kilometers per second. For Borisov, it was roughly 32 kilometers per second. Both values fit comfortably within models of how objects are ejected from planetary systems. During the formation of a solar system, planets migrate and interact gravitationally. These interactions can fling smaller bodies outward at high speeds. Models predict that most ejected objects should have excess velocities between 20 and 40 kilometers per second. Atlas exceeds this range significantly. Its excess velocity is approximately 48 kilometers per second. That places it at the high end of what natural ejection processes can produce. Not impossible, but unusual. The speed suggests that something energetic happened in Atlas's past. Perhaps it was ejected during a close encounter with a massive planet. Or perhaps it received gravitational boosts from multiple stars during its journey. Both scenarios are possible, but they require specific conditions. Scientists are working to model how such high velocities could arise naturally. The calculations are complex, involving interactions that might have occurred billions of years ago. But the models do provide pathways. Under certain conditions, a comet could be accelerated to these speeds through purely natural processes. Yet the speed also opens a door to other possibilities. Possibilities that are more speculative, but cannot be dismissed entirely without evidence. If an object were designed to travel between stars, speed would be essential. Interstellar space is vast, and even at 48 kilometers per second, crossing the distance between stars takes millions of years. A faster object reaches its destination sooner. It spends less time exposed to cosmic radiation and interstellar dust. It arrives before its systems degrade too much. This line of thinking is not mainstream, but it exists in the literature. Theoretical papers have explored what an interstellar probe might look like, how it might be designed to survive the journey, and how it might be disguised to avoid detection. One strategy suggested in these papers is to coat the probe in ice and dust, to make it appear natural, like a comet or asteroid. Such a disguise would allow the probe to pass through other solar systems without drawing attention. It would respond to sunlight by outgassing, just as a real comet would. It would appear in spectra as a mixture of ices and minerals. Only its velocity might hint at something unusual. A speed slightly higher than expected, explicable by natural processes, but also consistent with intentional design. Atlas's velocity does not prove anything. It remains within the realm of what nature can produce. But it sits at the edge of that realm, high enough to make scientists pause and consider whether there might be more to the story. The problem is that velocity alone cannot distinguish between natural and artificial. Both scenarios produce similar numbers. To determine which explanation is correct, scientists need additional data. They need to look at the object's behavior, its chemistry, and its response to solar heating. They need to watch it closely as it approaches the sun and see if anything changes. Speed is just the first clue. But it is an important one. It tells us that Atlas has experienced forces or conditions different from most objects we have studied. Whether those forces were random or intentional remains an open question, one that will require patience and careful observation to answer. Speed raises questions, but chemistry provides answers. By analyzing the light reflected and emitted by Atlas, scientists can determine what the object is made of. What they have found so far does not match any comet from our solar system. The composition of Atlas suggests formation conditions very different from those that created the comets orbiting our sun. Or perhaps it suggests something else entirely. When sunlight strikes a comet, something remarkable happens. The frozen ices on its surface begin to warm. Molecules that have been locked in place for billions of years suddenly gain energy. They break free from the solid surface and drift away as gas. This process, called sublimation, creates the glowing coma that makes comets visible. The gas scatters sunlight, creating a hazy envelope around the nucleus. Dust particles mixed with the ice also escape, forming a tail that streams away from the sun. For astronomers, this outgassing is not just beautiful. It is informative. The gases released by a comet carry chemical signatures that reveal what the nucleus is made of. By analyzing the light passing through the coma, scientists can identify specific molecules. Water, carbon monoxide, carbon dioxide, methane, ammonia. Each molecule absorbs and emits light at characteristic wavelengths. By measuring these wavelengths, astronomers can determine the comet's composition. For most comets in our solar system, water dominates. Water ice is abundant, and it sublimates readily when heated. Other molecules appear in smaller quantities, creating a diverse but predictable mixture. When Borisov, the second interstellar comet, was analyzed, it showed a composition similar to local comets. Water was the primary component, with carbon monoxide and other molecules present in expected ratios. This confirmed that comets in other star systems form through processes similar to those in our own. But Atlas is different. Very different. The composition of its coma has surprised scientists and raised questions that do not have easy answers. Let us examine what makes the chemistry of Atlas so unusual. Every comet carries within it a record of its birth. The molecules frozen in its nucleus tell the story of the conditions where it formed. Atlas tells a story unlike any we have heard before. A story written in carbon dioxide instead of water. When the James Webb Space Telescope turned its infrared instruments toward Atlas, astronomers expected to see familiar signatures. Water vapor is the hallmark of cometary activity. It appears prominently in nearly every comet observed from Earth. But the spectra returned by Webb showed something unexpected. Carbon dioxide dominated the signal. Water was present, but only in small amounts. The ratio was approximately 8 parts carbon dioxide to 1 part water. This composition is unprecedented. No comet from our solar system and no previously observed interstellar comet has shown such an extreme imbalance. Scientists immediately began searching for explanations. The first possibility is that Atlas formed in a very cold region of its parent star's planetary disk. In the outer reaches of a solar system, temperatures can drop low enough that carbon dioxide condenses before water does. If Atlas formed in such a region, its nucleus might be enriched in carbon dioxide relative to water. This explanation is plausible, but it requires specific conditions. The region would need to be cold enough for carbon dioxide to dominate, yet still contain some water. Models can produce such conditions, but they represent a narrow range of possibilities. The second possibility involves surface processing. Over billions of years, cosmic rays bombard interstellar objects. These high-energy particles can alter the chemistry of surface materials. They might break down water molecules more efficiently than carbon dioxide molecules. Or they might create a crust that seals water beneath the surface while allowing carbon dioxide to escape. If this happened to Atlas, the coma we observe might not reflect the true bulk composition of the nucleus. It might only show what is escaping from the surface layers. Again, this explanation is plausible, but it requires processes that operate over extremely long timescales. And it assumes that Atlas is ancient enough for such processing to have occurred. A third possibility involves insulating dust layers. If the nucleus is coated with a thick layer of dust, that dust might prevent water from escaping easily. Carbon dioxide, being more volatile, could still percolate through the dust and escape into space. This would create an apparent imbalance in the observed coma, even if the nucleus contains more water deeper down. All three explanations are scientifically sound. Each one could account for the unusual chemistry, but none of them feel entirely satisfying. The ratio is so extreme that it pushes the limits of what these natural processes can produce. And there is another detail that adds to the puzzle. Atlas became active unusually early. Most comets remain dormant until they approach within about 3 astronomical units of the Sun. At that distance, solar heating becomes strong enough to sublimate significant amounts of ice. Atlas, however, was already showing a detectable coma at more than 4 astronomical units. It was releasing gas before it should have been. This early activity is consistent with carbon dioxide domination. Carbon dioxide sublimates at lower temperatures than water. If the nucleus is rich in carbon dioxide, it would become active farther from the Sun. So the early activity supports the chemical observations. But it also raises a question. Why is this object so responsive to sunlight at such a great distance? Is it simply because of its composition? Or is there something else going on? Some researchers have quietly asked whether the chemistry could be intentional, whether the unusual ratio might serve a purpose beyond natural formation. This speculation is not widely discussed in official channels, but it appears in informal conversations and online forums. The idea is that an advanced civilization might engineer a probe to release specific gases. Gases that mimic natural cometary outgassing while serving other functions. Carbon dioxide, for instance, could be used for propulsion or temperature regulation. Or it could be chosen simply because it creates a convincing disguise. A probe coated in carbon dioxide ice would behave like a comet when approaching a star. It would sublimate, creating a coma that looks natural in spectra. But beneath that disguise, other systems could operate undetected. This idea remains speculative, far outside the scientific consensus. Most scientists favor natural explanations and consider artificial scenarios too unlikely to pursue seriously. But the unusual chemistry does leave room for the question. It creates a space where speculation can take root, even if evidence does not yet support it. For now, the chemistry of Atlas stands as an anomaly. Explainable, but barely so. Fitting within natural models, but only at the edges of probability. It is one more detail that makes this object different. One more reason why Atlas has captured the attention of scientists and the imagination of the public. Chemistry tells us what Atlas is made of. But to understand what it means, we need context. We need to compare it to the other interstellar visitors we have encountered. Only by placing Atlas alongside Oumuamua and Borisov can we see how unusual this third visitor truly is. Before Atlas, humanity had encountered 2 confirmed visitors from interstellar space. Each arrival was significant, each brought its own mysteries. But together, they seem to tell a reassuring story. That interstellar objects are natural debris, ejected during planetary formation. That they pose no threat and hold no surprises beyond what science can explain. Atlas challenges that comfortable narrative, not by proving it wrong, but by showing how incomplete it might be. Oumuamua arrived first, in October 2017. It was detected by the Pan-SDARS telescope in Hawaii, moving on a hyperbolic trajectory that confirmed its interstellar origin. But Oumuamua refused to fit neatly into any category. It showed no visible coma, suggesting it was not releasing gas like a typical comet. Yet it accelerated slightly as it moved away from the sun, as though something was pushing it. The most likely explanation was outgassing too faint to detect visibly. But the absence of a visible coma left room for speculation. Some suggested Oumuamua might be a fragment of a shattered planet. Others proposed it could be an artificial object, perhaps a derelict probe or a light sail. These ideas were controversial, widely dismissed by most scientists. But they captured public imagination and shaped how people thought about interstellar visitors. Then came Borisov, discovered in August 2019 by an amateur astronomer in Crimea. Borisov was everything Oumuamua was not. It displayed a bright coma rich in familiar molecules. Its composition matched expectations for comets formed in other solar systems. It behaved predictably, increasing in brightness as it approached the sun and fading as it receded. Borisov reassured the scientific community. It suggested that most interstellar objects would be ordinary, that Oumuamua's strangeness was an exception. But now comes Atlas. Faster than either predecessor, chemically stranger than both, active earlier than expected, and potentially older than our entire solar system. To understand what Atlas represents, we must see how it compares to what came before. Each interstellar object tells a story. Oumuamua spoke in riddles. Borisov spoke clearly. And Atlas speaks in a language we are still learning to understand. Oumuamua, the first confirmed interstellar visitor, was a puzzle from the moment it was discovered. Its shape was unusual, elongated, perhaps 10 times longer than it was wide. Observations showed it tumbling as it moved, rotating in a complex pattern. Its brightness varied dramatically as different sides faced Earth, suggesting an irregular, possibly cylindrical form. No comet or asteroid from our solar system had ever displayed such extreme elongation. The shape alone generated speculation. Was it a natural fragment, broken off from a larger body? Or could it be something designed, an artifact with an intentional structure? Then came the acceleration. As Oumuamua moved away from the sun, it accelerated slightly. Not much, but enough to be measurable. This kind of acceleration is typical for comets. As they heat up, they release gases that push them like tiny rockets. But Oumuamua showed no visible coma, no detectable outgassing, no signs of the activity that should accompany such acceleration. Scientists proposed that the outgassing might be too faint to see, or that it was releasing gases from composition different from typical comets. Water-free ices, perhaps, that sublimate without creating a visible cloud. These explanations were plausible, but they stretched the boundaries of what comets normally do. And they left enough uncertainty for speculation to flourish. Harvard astronomer Avi Loeb famously suggested that Oumuamua might be an artificial light sail, a thin, reflective structure pushed by starlight, explaining both its shape and its acceleration. Most scientists rejected this idea, favoring natural explanations. But the debate brought attention to a simple fact. We cannot always distinguish between the natural and the artificial based on limited observations. Sometimes unusual behavior can be explained either way. Oumuamua left the solar system before more detailed observations could be made. Its mysteries remain unresolved. Borisov, by contrast, was straightforward. It appeared as a classic comet from the moment it was discovered. A bright coma surrounded its nucleus. Spectroscopic observations showed water, carbon monoxide, and other familiar molecules. Its light curve behaved predictably, brightening as it approached the sun. Near perihelion, it fragmented slightly, a common occurrence for comets under thermal stress. Everything about Borisov fit within established models of cometary behavior. It confirmed that other star systems produce comets similar to our own, that the processes of planetary formation are universal. For many scientists, Borisov was proof that most interstellar objects would be normal. That Oumuamua was an outlier, an exception that proved the rule. But Atlas disrupts this simple narrative. It is not as ambiguous as Oumuamua. It clearly shows cometary activity, a coma visible in images and spectra. But its composition is wrong. Carbon dioxide dominates where water should. And its speed is too high, nearly twice that of Borisov. Its trajectory suggests origins in an ancient population of stars. Stars that formed when the Milky Way was young and violent. If true, Atlas has been traveling for billions of years. Longer than Borisov, longer than Oumuamua, longer than Earth has had oceans. Comparing the three visitors reveals a pattern, or perhaps the absence of one. Each object is different. Each challenges expectations in its own way. Oumuamua was strange in shape and acceleration. Borisov was normal in almost every respect. Atlas is strange in chemistry and speed. Together, they suggest that interstellar space is filled with diversity. That no single model can predict what these visitors will look like. Some will be ordinary, others bizarre. And a few, perhaps, will defy explanation entirely. The question is whether this diversity is purely natural. Whether random ejections from countless planetary systems inevitably produce a wide range of objects. Or whether some of these visitors might have origins we have not yet seriously considered. The three objects do not provide enough data to answer that question, but they provide enough strangeness to keep it alive. Each new interstellar visitor adds to our understanding, but each also adds to the list of things we cannot yet explain. Atlas is the latest chapter in this unfolding story, and like the chapters before it, it leaves us with more questions than answers. The comparisons raise a deeper question. Are we seeing more interstellar objects because they are becoming more common? Or are we simply getting better at noticing them? The answer matters because it shapes how we interpret what we are seeing. In 2017, the discovery of Oumuamua felt like a once-in-a-generation event. An interstellar object passing through our solar system seemed almost impossibly rare. Then, just 2 years later, Borisov appeared. And now, 6 years after that, we have Atlas. 3 confirmed interstellar visitors in less than a decade. This frequency raises an important question. Has something changed? Are these objects arriving more often than before? Or have we simply become better at finding them? The answer lies in our technology. Telescopes have improved dramatically over the past 20 years. Automated survey systems now scan the entire sky regularly. Computers process images faster, identifying moving objects within hours of observation. Networks of observatories coordinate globally, confirming discoveries and refining orbits. Before these systems existed, interstellar objects could pass through our solar system unnoticed. They are faint, moving quickly, and easily mistaken for distant asteroids or comets on ordinary orbits. Without precise measurements and rapid follow-up, they would simply blend into the background. Now we catch them. Not all of them, certainly. Many still pass undetected, but enough to realize that interstellar objects are not rare anomalies. They are common features of the galaxy. Models suggest that at any given time, several interstellar objects are passing through our solar system. Most are too small or too faint to detect, but they are there, drifting silently through the space between planets. This realization changes the context of Atlas. It is not an isolated mystery. It is one member of a vast population. A population we are only beginning to study. And within that population, the possibility exists that not all objects are purely natural. Let us explore what that possibility means. Science operates on evidence and observation. But sometimes, evidence creates space for questions that feel uncomfortable. Questions about whether we are observing something beyond natural processes. With Atlas, that question has emerged quietly in scientific discussions. The idea that an interstellar object might be artificial is not new. It has been explored in scientific literature for decades. Papers have been published examining what an interstellar probe might look like, how it would travel, how it would survive, and how it might be detected. These papers are theoretical, thought experiments exploring possibilities. They do not claim that such objects exist, but they establish that the question is scientifically legitimate. When an object exhibits unusual characteristics, it is reasonable to consider all explanations. Natural explanations should always be favored when they fit the data. But when an object displays multiple anomalies, each one pushing the boundaries of natural models, the question of alternatives becomes relevant. Atlas presents several such anomalies. Its speed is unusually high, but explainable through natural ejection processes. Its chemistry is unprecedented, but could result from specific formation conditions. Its early activity is surprising, but consistent with carbon dioxide-rich composition. Individually, each anomaly has a natural explanation. But together, they create a profile that sits at the edge of what we consider normal. This is where speculation begins. Not because any single piece of evidence points to artificial origin, but because the combination of unusual features creates a pattern worth considering. One theoretical scenario involves a probe disguised as a comet. An advanced civilization wishing to explore other star systems might choose stealth over announcement. A probe coated in ice and dust would appear natural in telescopes. It would sublimate under solar heating, creating a convincing coma. Its trajectory would follow the laws of physics, betraying nothing unusual. Only close examination might reveal inconsistencies. Chemistry slightly wrong for natural formation. Activity patterns that do not quite match models. Velocity suggesting energetic origins. None of these would prove artificiality on their own. But together, they might hint at something beneath the surface. Another scenario involves ancient technology. A probe launched billions of years ago by a civilization that no longer exists. Such an object would bear the marks of age. Its surface processed by cosmic radiation over geological time. Its systems dormant, perhaps, or operating on automatic protocols. It would not communicate because there is no one left to receive the message. It would simply continue its programmed path, a ghost of a civilization lost to time. These scenarios are speculative, sitting far outside mainstream scientific consensus. Most scientists dismiss them as unnecessary complications. Natural explanations are sufficient, they argue, and invoking artificial origins without direct evidence is unscientific. This position is reasonable and represents the majority view. But a small number of researchers keep the question open, not because they believe Atlas is artificial, but because ruling out the possibility without investigation would be premature. The challenge is determining what evidence would actually distinguish natural from artificial. With current technology and limited observation time, the distinction may be impossible to make. A perfectly disguised probe would be indistinguishable from a natural comet. Its chemistry might be slightly unusual, but still within the range of natural possibilities. Its behavior might be subtly different, but not enough to prove anything. Only direct examination, a mission to intercept and study the object closely, would provide definitive answers. But such a mission is beyond our current capabilities. Atlas is moving too fast, and it will leave the inner solar system long before we could design and launch an intercept. So we are left with telescopic observations and speculation. Data that fits natural models, but leaves room for questions. The importance of asking these questions is not about proving alien technology exists. It is about maintaining scientific openness, about not dismissing possibilities simply because they make us uncomfortable. Throughout history, science has advanced by considering ideas that seemed unlikely. Continental drift, black holes, quantum entanglement, all were dismissed before evidence accumulated. The question of artificial interstellar objects may follow a similar path. Most such objects will be natural. But if even one is not, detecting it would be among the most significant discoveries in human history. For now, Atlas remains classified as a natural comet. An unusual one, certainly, but still within the bounds of what nature can produce. The question of artificial origin remains speculative, supported by curiosity rather than evidence. But it remains a question worth keeping in mind as we continue to observe. Because the universe has surprised us before, and it will almost certainly surprise us again. Whether natural or otherwise, Atlas is approaching a critical moment. On October 29, 2025, it will reach perihelion, its closest approach to the Sun. That moment will subject the object to intense solar heating. Whatever secrets lie within its frozen nucleus may be revealed when that heat arrives. Scientists around the world are preparing their instruments for that day. Every comet has a moment of truth, a point in its orbit where the sun's heat reaches maximum intensity. For some comets, this moment brings spectacular displays, tails stretching millions of kilometers across space, brightness increasing until the comet becomes visible to the naked eye. For others, the moment brings fragmentation. The nucleus splits apart under thermal stress, crumbling into pieces that slowly separate and fade. And for a few, the moment brings revelation. Hidden ices sublimate, revealing layers beneath the surface. Chemical signatures change as different materials are exposed. Activity increases or decreases in ways that test our models. For Atlas, perihelion arrives on October 29, 2025. At that moment, it will be roughly 140 million kilometers from the Sun. Closer than Earth's orbit, but not dramatically so. The distance is similar to where many ordinary comets begin showing strong activity. But Atlas is not an ordinary comet. Its unusual chemistry means scientists cannot predict exactly how it will respond. Will the carbon dioxide activity intensify? Will hidden water ice beneath the surface finally begin to sublimate? Will the nucleus remain intact, or will thermal stress cause it to fragment? These questions will be answered in real time as telescopes watch. The James Webb Space Telescope has observation time scheduled. Hubble will capture images as the object brightens. Ground-based observatories around the world will track its position and measure its spectra. Amateur astronomers with backyard telescopes may even glimpse it as a faint smudge against the stars. Perihelion is not just a scientific milestone. It is a moment of potential revelation. A chance for Atlas to show us what it truly is, or to deepen the mystery by behaving in ways we did not anticipate. Let us consider what might happen when that moment arrives. In astronomy, predictions are made with precision. But comets have a way of defying those predictions. Atlas will soon face the Sun's full intensity. What happens next could confirm everything we think we know. Or it could change everything. Perihelion is the point in an orbit where an object comes closest to the Sun. For comets, this is the most important moment in their journey through the inner solar system. Solar radiation reaches its peak intensity. Temperatures on the nucleus surface can rise to several hundred degrees above the freezing point of water. Ices that remained stable farther out begin to sublimate rapidly. The coma expands, sometimes dramatically. Tails stretch outward, pushed by solar wind and radiation pressure. This is when comets become most active and most visible. For Atlas, perihelion will occur at a distance of approximately 1.4 astronomical units. That is about 210 million kilometers from the Sun, slightly farther than the distance where Earth orbits. At this distance, solar heating will be strong but not extreme, enough to drive significant sublimation of volatile ices, but not enough to cause catastrophic disruption for a typical comet. The question is whether Atlas is typical. Its carbon dioxide-rich composition means it should already be active at this distance. Carbon dioxide sublimates at lower temperatures than water. By the time Atlas reaches perihelion, much of its surface carbon dioxide may have already been released. If so, the intensity of activity might not increase as much as expected. Or, alternatively, the heating might expose deeper layers. Layers where water ice has remained frozen beneath a carbon dioxide crust. If water begins to sublimate, the chemical signature of the coma will change. The ratio of carbon dioxide to water might shift toward more balanced levels. This would provide important information about the nucleus structure. Scientists will be watching for exactly this kind of change. Another possibility is fragmentation. Comets can break apart when thermal stress creates cracks in the nucleus. As ice sublimates from within, pressure builds. If the nucleus is weak or already fractured, that pressure can split it into multiple pieces. This happened to comet Shoemaker-Levy 9 when it passed close to Jupiter. Tidal forces and internal stresses tore it into more than 20 fragments. Something similar could happen to Atlas, though on a smaller scale. If the nucleus fragments, it would tell us something about its internal structure. A strong, monolithic body would remain intact. A loosely bound rubble pile would break apart more easily. Observing how Atlas responds to perihelion stress would reveal which type it is. Telescopes are prepared for multiple scenarios. If the comet brightens significantly, rapid follow-up observations will capture the increased activity. If it fragments, images will track how the pieces separate and evolve. If its chemistry changes, spectrographs will measure the new molecular signatures. And if something unexpected happens, something that does not fit any model, that will be recorded too. The public will be watching as well. News outlets are already preparing coverage of the perihelion event. Social media will amplify whatever images and data are released. If Atlas behaves normally, interest will fade quickly. But if it does something unusual, speculation will intensify. There is a small but vocal group of people who believe Atlas might be more than a comet. They are waiting for perihelion, hoping for evidence that supports their suspicions. A sudden change in trajectory, perhaps, or the appearance of structures within the nucleus, or communication signals that activate when solar energy becomes available. Scientists consider these scenarios extremely unlikely. The overwhelming evidence points to a natural object. But the attention serves a purpose. It reminds us that when we observe something unusual, we must remain open to all possibilities, even the ones that seem far-fetched. For the scientific community, perihelion is primarily an opportunity to gather data. Data that will help refine models of cometary behavior. Data that will improve our understanding of how ices sublimate under solar heating. Data that will reveal the internal structure and composition of an interstellar comet. These goals are modest but important. They represent the steady accumulation of knowledge that defines scientific progress. But there is also a deeper significance to this moment. Atlas is one of only 3 interstellar objects ever studied in detail. Every measurement we make adds to our limited understanding of what exists beyond our solar system. Every observation helps us learn what other star systems produce. And every piece of data brings us closer to answering fundamental questions about the galaxy. Are interstellar objects purely natural debris? Or might some carry signatures of intelligence? Do other civilizations exist? And if so, what traces might they leave behind? These questions cannot be answered by observing a single comet. But each observation contributes to a larger picture that is slowly coming into focus. October 29th will be a day of careful watching. Telescopes will track Atlas as it rounds the sun. Scientists will analyze data as it arrives. And somewhere in that data might be the detail that shifts our understanding. Or perhaps not. Perhaps Atlas will behave exactly as models predict. Perhaps it will confirm that we already understand cometary physics well enough. Either outcome will be valuable, because science advances not only through surprises. It also advances through confirmation, through the steady verification that our models work. We will know soon enough. The countdown to perihelion continues, and the universe, as always, will reveal only what it chooses to reveal. After perihelion, Atlas will begin its long journey outward. It will fade from view as it moves away from the sun. Within months, it will be too distant for detailed observation. Within years, it will leave our solar system entirely. And humanity will be left to interpret what we observed during its brief passage. But the story of Atlas extends beyond the object itself. It connects to larger questions about what fills the space between stars, and what that means for our understanding of the galaxy. The galaxy is vast, beyond comprehension. 400 billion stars, possibly more. Each star potentially surrounded by planets. Each planet potentially producing debris during formation. The mathematics of planetary formation suggest that vast numbers of objects get ejected. Gravitational interactions between forming planets fling smaller bodies outward. Some fall into the star, others settle into stable orbits. But many are thrown out entirely, escaping into interstellar space. Models estimate that for every star system, thousands or even millions of objects might be ejected. Multiply that by the number of stars in the galaxy. The result is a population almost too large to imagine. Trillions upon trillions of objects drifting through the dark between stars. Most are small, a few meters across or less. But some are larger, kilometers in diameter. They travel at speeds determined by their ejection velocity and subsequent gravitational encounters. Most move slowly relative to the galaxy's rotation. But some, like Atlas, move faster, accelerated by multiple interactions over billions of years. At any given moment, several of these objects are passing through our solar system. We detect only the largest and brightest. The rest remain invisible, too faint for our telescopes to notice. This vast population of interstellar objects represents a kind of galactic traffic. Debris constantly moving between star systems. Most of it natural, the inevitable result of planetary formation. But within such a large population, other possibilities exist. Statistical possibilities that become relevant when the numbers are large enough. Let us explore what those possibilities might be. When the number of objects is measured in trillions, probabilities change. Events that seem unlikely in small samples become inevitable in large ones. The question is not whether something unusual exists among the interstellar population. The question is whether we could recognize it if we saw it. Imagine a civilization that achieves interstellar travel. Not through massive ships carrying living beings, but through small, automated probes sent to explore other star systems. The strategy makes sense from an engineering perspective. Small probes require less energy to accelerate. They can be mass-produced and sent in large numbers. Losses are acceptable because many will reach their destinations. Such a civilization might send thousands or millions of probes, each one targeted toward a different star system, each designed to observe, record, and perhaps transmit data back to the origin. Now imagine that this civilization launched its probes billions of years ago, long enough that the civilization itself may no longer exist. But the probes continue, following their programming, drifting through space on trajectories set eons ago. Most would be destroyed over such timescales. Collisions with dust, degradation from radiation, failures in their systems. But a few might survive, especially if they were designed with durability in mind. Coated in ice and dust to protect delicate systems. Powered by long-lived isotopes or solar energy harvested during close approaches to stars. Silent to avoid detection by potentially hostile species. These surviving probes would be indistinguishable from natural objects. They would look like comets or asteroids. They would follow trajectories determined by gravity. They would sublimate and outgas when heated by sunlight. Only detailed examination might reveal anomalies. Chemistry slightly wrong. Structure suggesting design rather than random accretion. Responses to heating that do not quite match natural models. This scenario is speculative, but it is based on reasonable assumptions. If technological civilizations exist, they might explore the galaxy this way. And if they do, the probes they send would blend into the population of natural interstellar objects. Hidden in plain sight among trillions of pieces of debris. The challenge is detection. How would we identify an artificial object among so many natural ones? The answer is that we probably would not, unless the object revealed itself through obvious anomalies. Most artificial probes, if they exist, would be designed to remain hidden. Stealth would be a primary design criterion, not to avoid detection in an aggressive sense, but simply because revealing oneself to unknown species carries risks. This is the logic behind the dark forest hypothesis. The idea that the galaxy might be filled with civilizations, all remaining silent to avoid attracting attention. In such a scenario, exploration would occur through passive observation. Probes that watch without announcing their presence. Gathering data without interference. If this hypothesis is correct, then interstellar objects take on new significance. Each one could potentially be more than it appears. Not all of them, certainly. The vast majority would still be natural, but a small percentage might be remnants of exploration efforts. Ancient technology coated in ice, drifting silently through space. Watching civilizations that do not yet know they are being watched. Atlas fits this profile in unsettling ways. Its unusual chemistry could be natural, or it could be a signature of artificial composition. Its high velocity could result from natural ejection or from intentional design. Its early activity could reflect volatile ices or systems activating in response to solar energy. None of these observations prove anything, but they keep the possibility alive. The possibility that what we are observing is not entirely natural. For scientists, this possibility must be handled carefully. Claiming that Atlas is artificial without evidence would damage credibility. It would invite ridicule and undermine serious scientific work. But dismissing the possibility without investigation would be equally problematic. If artificial interstellar probes exist, finding one would be transformative. It would prove that other technological civilizations have existed. It would provide insight into their engineering and their motivations. It would fundamentally alter our understanding of our place in the universe. The scientific approach is to remain neutral, to favor natural explanations while keeping the door open to alternatives, to continue observing and gathering data, and to wait for evidence that might tip the scales one way or the other. For now, Atlas remains a comet. Unusual, certainly, but still explicable within natural frameworks. The idea that it might be something more remains speculative. A possibility suggested by unusual characteristics, but not proven by them. Yet the very existence of this possibility changes how we view interstellar objects. They are no longer just debris from distant planetary systems. They are potential messengers, windows into processes and perhaps intelligences that exist beyond our solar system. Every new interstellar object we detect adds to our understanding. And every one forces us to ask the question again. What are we really seeing? The question of artificial origins leads naturally to another consideration. If some interstellar objects might be probes, what purpose would they serve? What would they be designed to observe? And if they are watching us, what might they be learning? Observation is the foundation of science. We learn about the universe by watching it. Telescopes capture light from distant stars and galaxies. Probes visit other planets, sending back images and data. Even on Earth, we observe ecosystems to understand how they function. The act of watching without interfering provides valuable information. It reveals behavior in natural contexts, unaltered by the presence of the observer. If another civilization wished to study us, they might use the same approach. Observe from a distance without announcing their presence. Gather data over long periods to see how our civilization develops. Record our technological progress, our social structures, our responses to challenges. An interstellar probe passing through our solar system would be ideally positioned for such observation. It could monitor radio transmissions, measuring our communication patterns. It could observe changes in our atmosphere, detecting pollution and industrial activity. It could track the movement of satellites and spacecraft, assessing our technological level. All of this could be done passively, without revealing the probe's true nature. To us, it would appear as nothing more than a comet. Unremarkable, except for a few unusual characteristics. This scenario is deeply unsettling because it suggests asymmetry. If we are being observed, we are the subjects of study. We have no control over what is recorded or how it is interpreted. And we may never know the observation occurred. Atlas, if it were such a probe, has already gathered significant information. It has passed through our planetary system during a critical period in human development. It has arrived at a moment when we are technologically advanced enough to detect it, but not advanced enough to intercept or examine it closely. From an observational perspective, this is an ideal time. We reveal our capabilities through detection and analysis, but we cannot interfere with the observation process. Let us consider what such an observation might mean. Every question we ask about Atlas reveals something about us. Our curiosity, our fears, our level of understanding. If something is watching, then we are the data being collected. And what we do next might be the most revealing observation of all. Human responses to the unknown follow predictable patterns. When something unfamiliar appears, we seek to categorize it. We compare it to things we already understand. We create narratives that make the unknown feel manageable. With Atlas, these patterns are clearly visible. Scientists frame it as an unusual comet, interesting but explainable. They emphasize natural processes and downplay speculation. This response reflects training and methodology. Science requires evidence before conclusions, and evidence for artificial origin is absent. But outside scientific circles, the response is different. Online communities discuss the possibility of alien probes. They analyze every piece of data, looking for anomalies. They create theories that range from plausible to fantastical. This response reflects human imagination and the desire for meaning. Both responses are revealing. They show how our species handles uncertainty. Some seek comfort in conventional explanations. Others seek excitement in unconventional possibilities. Neither approach is wrong, but together they paint a picture of a civilization grappling with its place in the universe. If Atlas were an observational probe, this response would be valuable data. It would show that humanity has reached a stage where it can detect interstellar objects. But it would also show that we are divided in how we interpret them, that we lack consensus on questions that extend beyond immediate scientific evidence. Our technological capabilities would be evident. Telescopes powerful enough to detect objects at great distances. Computers capable of calculating complex orbital trajectories. Instruments sensitive enough to analyze chemical compositions. These capabilities mark us as a species approaching technological maturity. But our responses would also reveal vulnerabilities. The tendency towards speculation without evidence. The ease with which narratives spread through social media. The division between scientific consensus and popular belief. These characteristics might indicate a civilization still learning to manage information. Another revealing aspect is how we communicate about Atlas. News articles emphasize the unusual characteristics while downplaying concerns. Social media amplifies both wonder and fear. Official statements from space agencies prioritize reassurance. This pattern shows a species aware of its own anxiety about the unknown. A species that tries to manage public perception while seeking truth. If an observing intelligence were analyzing these communications, what conclusions might it draw? Perhaps that humanity is cautious, preferring to minimize panic even when faced with mystery. Perhaps that we are curious, willing to study things we do not fully understand. Perhaps that we are divided, unable to agree on how to interpret ambiguous evidence. All of these conclusions would be accurate. They would reflect the complexity of human civilization in the early 21st century. There is also the question of what we do not do. We do not attempt to communicate with Atlas. We do not send signals toward it, testing whether it might respond. This restraint might reflect scientific caution, or it might reflect an instinctive understanding that revealing ourselves carries risks. Either way, the choice to observe silently rather than interact reveals something about our priorities. We prefer to learn before we engage, to understand before we commit to action. This could be interpreted as wisdom or as hesitation. The significance depends on the perspective of the observer. If Atlas is truly just a comet, then these observations are meaningless. We are simply studying a natural object, and our responses reflect ordinary scientific process. But if it is something more, then every action we take is part of the data set. Every measurement, every debate, every news article becomes information about humanity. Information that might be recorded, analyzed, and stored. Not for immediate use, but perhaps for future reference. This possibility adds weight to the experience. It transforms observation from a passive activity into a form of contact. Contact that occurs not through communication, but through revelation. We reveal ourselves simply by being ourselves, by responding to the unknown in ways that reflect our nature. And if something is watching, It learns about us not from what we say, but from what we do when we think no one is listening. The question then becomes philosophical rather than scientific. Does it matter whether Atlas is natural or artificial? If our response to it reveals the same truths about humanity either way. Perhaps the real test is not whether we detect alien technology, but whether we can handle the uncertainty of not knowing. Whether we can continue observing, questioning, and learning without demanding immediate answers. This ability to sit with mystery is itself revealing. It shows whether a civilization has matured beyond the need for constant certainty. Whether it can function in a universe where not everything is immediately explainable. Atlas will leave our solar system soon. Within months, it will fade from view. Within years, it will be beyond the reach of our most powerful telescopes. We will be left with the data we collected and the questions we could not answer. And somewhere in that data, recorded in images and spectra and orbital calculations, lies a portrait. Not just of a comet, but of ourselves. Of how we respond when the universe delivers something unexpected. Of what we reveal when we think we are the ones doing the watching. Atlas continues its journey outward from the sun. Its path is calculated, its future trajectory known. In a few months, it will pass beyond the orbit of Mars. In a few years, it will leave the inner solar system entirely. Eventually, it will return to interstellar space, continuing a journey that may have lasted billions of years. We will watch it for as long as our telescopes can track it, gathering data, refining measurements, testing theories. And when it finally fades from view, we will be left with what we learned. Not just about the comet, but about the galaxy that produced it. About the processes that create and eject objects from planetary systems. About the chemistry possible under conditions different from those in our own corner of space. But we will also be left with questions. Questions about whether everything we observed has a natural explanation, or whether some details hint at possibilities we are not yet ready to fully consider. These questions will not be resolved by Atlas alone. They will require more observations, more interstellar visitors, more data. Each new object we detect adds to our understanding. Each one either confirms that natural processes explain everything, or adds to the accumulation of anomalies that might eventually point elsewhere. For now, Atlas remains what we call it: a comet. Unusual in composition, exceptional in speed, but still a comet. The possibilities scientists are watching closely are just that. Possibilities, not certainties. Questions, not answers. And perhaps that is exactly as it should be. Science does not advance through immediate certainty. It advances through careful observation, patient analysis, and the willingness to remain open. Open to new data, new interpretations, new questions. If Atlas has taught us anything, it is that the universe still holds surprises. That even in an age of advanced telescopes and detailed models, we can still encounter something that makes us pause. Something that reminds us how much we have yet to learn. October 29th will come and go. The data from perihelion will be analyzed and published. And Atlas will continue outward, carrying its secrets with it. Whether those secrets are purely geological, chemistry frozen in ice from another star system, or something more, something we can only speculate about, remains to be seen. Thank you for exploring this mystery with us. If this journey through the questions surrounding Atlas brought you wonder, curiosity, or simply a moment of calm reflection, we are grateful you were here. The universe will continue to deliver mysteries, and we will continue to watch, to wonder, and to explore what they might mean. Until the next discovery, rest well. Let your thoughts drift like comets through the darkness. And remember that sometimes the most important questions are the ones we ask rather than the ones we answer.